Yeah, Aman, I have a doubt session in one of the lectures this week. But yeah, I forgot to tell you that in that doubt session, I also intend to discuss the the MT7, any doubts if you have from that, along with, of course, doubts from the current topics. So I don't think we have discussed the MT7 paper yet in class. So if you have any doubts pending from that, I think it is either tomorrow or day after, one of the days in the morning, we have a doubt session. So we'll discuss that during the doubt session. Okay, so first law of thermodynamics. We had seen the statement. The way we write it in physics is slightly different because we write the work done term as the work done by the gas. So Q is equal to delta U plus W, where delta U is that N into degrees of freedom into half RT, R delta T term. This is the state function, whereas the other two are the path functions. The important thing is W is the work done by the gas, so it is integration PdV here. So W is positive for an expansion and W is negative for a compression. Whereas if you have also seen that in another way, you can write this as Q plus work done, but I'll write that as W prime is equal to delta U. But in that case, your W prime is not work done by the gas, it is work done on the gas. Okay, so it really depends on how we are expressing the work done term. So that becomes minus integration of PdV. So work done on the gas, that is positive for compression and it is negative for expansion. Whereas if we write it as work done by the gas, then it's the other way around. So this is something that we had discussed in the previous lecture. Just giving you a quick recap of that. And also graphically, in terms of the PV space, W is the area under the PV graph. Okay. Such that again, this sign convention we have to stick to. It is positive of the area if it is an expansion and negative of the area if it is a compression. Okay, so that's that. Then the term Q. So W, as you can see, because it is a term defined by integration PdV, it becomes a path function. So accordingly, Q also becomes a path function. Okay. So now keeping in mind that this definition of work done, it is applicable to a certain type of process, and that type of process is one where the pressure is uniform throughout the volume of the gas, and that happens in a situation where you can describe the work done as speed, integration PdV, or area under the PV graph only when we are talking about a particular type of process which is specific for a quasi-static process. That means almost static. And by definition, any quasi-static process is also reversible. Okay. Whereas this definition of delta U, it comes from kinetic theory of gases. So it is applicable to any ideal gas which displays or it obeys the principle of the ideal gas equation, PV is equal to nRT. Yeah, Somarup, F is the degrees of freedom. F is the degrees of freedom, which is 3 for monoatomic gas and 5 for diatomic gas. You remember, no? We have discussed in kinetic theory of gases. Okay, good. Right. So Q also becomes a path function accordingly. So We had seen an example of this application last time where we saw that we can calculate the work done by the area under the graph. We can calculate delta U by formula because it's a state function. And then we can use the formula of the first law of thermodynamics, that is Q is delta U plus W, to calculate the net work done. So that all we have seen. Now today let us first of all start with the understanding of the standard named processes or the four standard type of processes. So the first one, as you know, is Isochoric process. So I'll go over this quite fast because we've done this in chemistry. So this is one where volume is constant or the change in volume is zero. So in PV space, this process looks like a vertical straight line. So if volume is constant, that means also pressure is proportional to temperature. Okay, so therefore, in this graph, A to B is an isochoric heating process. We are heating the gas because temperature at B is greater than temperature at A. Whereas if we go from B to A, it is an isochoric cooling. Okay, temperature at A is less than temperature at B. So pressure is proportional to temperature. That's why volume being constant, the graph looks like this. And secondly, pressure being constant, volume being constant, the work done becomes zero because okay. So this completely makes sense because if you visualize experimentally what an isochoric process looks like, it's very simple. The experimental understanding of an isochoric process would be that you have a container of fixed volume, container. So if you supply any heat to this, then what will happen? The internal energy, if Q is positive, that means the internal energy will increase because the kinetic energy of gas molecules will increase, and that Q will be equal to delta U, will be a positive quantity. Okay. Similarly, so that's an example of an isochoric heating process. So what we'll observe is that temperature will increase with heat supplied. Okay. On the other hand, if we have a process where we are removing heat from the gas, you will see that the gas cools down. So if we have some way of absorbing heat, then we will see that heat is absorbed from the gas. So its internal energy will decrease because the kinetic energy of molecules decreases. So delta U will be negative. So this is an example of an isochoric cooling, that we have a container of fixed volume, and from that we are withdrawing heat by some mechanism from the gas inside. So the gas will cool down. Okay. So these are the two types of processes within isochoric heating and isochoric cooling. Okay. Now because work done is zero, so you can see that in this case, Q will be equal to delta U will be equal to a negative quantity. Okay. So these are the two types of situations. So this example here would be B to A, whereas here the example would be, in terms of the graph, it would be A to B. Okay. So further from first law, you can see that Q is equal to delta U is equal to NF by 2R delta T. whereas W is 0. Okay. So that is why we say that Q over here is NCV delta T, and that is equal to NF by 2R delta T. So we get the formula that CV is equal to F by 2R. CV being the isochoric molar specific heat capacity, and that has a value of 3 by 2R for noble gases or monoatomic gases, and it has a value of 5 by 2R for diatomic gases. Okay. So I think you're well aware of these things from chemistry, so don't need to really note down in so much detail and things. Just make sure that you remember all these things properly and you're familiar with the concept. So when we come to the application questions, you are able to follow without difficulty. So if we want, the process, like for example, we want an isochoric heating, which I've shown on the right hand side, to occur such that the process follows this graph. So we have to supply the heat very slowly so that the graph goes from the state of the gas goes from one point to another point to another point. And in each point in between, the gas is in some kind of equilibrium state. So that is why it is called a quasi-static process. We don't want a situation where we are suddenly applying a lot of heat to it and the temperature changes unevenly inside the gas. Because if that happens, then we cannot predict what kind of state the gas is in that intermediate stage. So we cannot really plot the graph of how the gas reached from state A to state B. So we want the graph to progress in this ordered manner systematically from point to point along that vertical line. We have to supply the heat very slowly, a little bit of heat at a time, so that the gas's temperature increases, the molecules stabilize at a certain average kinetic energy. Then further heat is supplied, so again the gas stabilizes at a higher temperature. And like that from point to point, you are going on the graph from A to B, and each point in between is a state of almost static equilibrium or quasi-static kind of state. Only then we can say that the behavior of the graph is behavior of the gas in the experiment is according to the graph that we are showing over here. Sudden changes will not result in this kind of situation where uh, you can predict the state of the graph at every point in between from initial to final. So that is the significance of quasi-static process that you should understand. Anybody has a doubt in this formula or application or anything, you can ask me. You can unmute yourself and ask me directly also, or you can text me, whichever is convenient. Okay, so that's the isochoric process. So the few things you should remember about isochoric is obviously volume is constant. That's one thing you should remember. So pressure is proportional to temperature. That directly comes from PV equal to nRT. Okay, then volume is constant. So work done is zero because the definition of work done is like this. So from your first law of thermodynamics, Q is equal to delta U plus W. You can see that if W is zero, then Q is equal to delta U. So this formula comes about. Okay. And you should remember that graphically it looks like on the PV space, it looks like a vertical line. To understand experimentally what we are doing, so keep the volume constant while we are doing any thermodynamic process or applying any thermodynamic process. You have to put the gas in a container which is of fixed volume. And then according to whether we are heating or cooling, we can supply heat from it or absorb heat from it, supply heat to it or absorb heat from it, and accordingly the gas will function according to the isochoric process. Okay, now next let's come to the isobaric process. Okay, so bar, as you know, is a unit of pressure, so it's easy to understand. Isobaric means constant pressure. Okay, so if we expand a gas at constant pressure, it is called an isobaric heating or an isobaric expansion. And if we compress the gas at constant pressure, it is called an isobaric compression. So volume becomes proportional to temperature from PV equal to nRT. Okay. Or during an isobaric expansion or compression, V1 upon V2 is equal to T1 upon T2 at two different points in between. on the graph. So isobaric pressure, isobaric process looks like a horizontal line at constant pressure. So at some pressure P naught, let's say, this volume is V1 and this volume is V2. So this A to B is an example of isobaric expansion because V2 is greater than V1, whereas B to A would represent an isobaric compression. Okay. So because pressure is constant implies PV equal to nRT can be interpreted as P delta V is equal to nR delta T, or work done, which is integration P dV, becomes, because pressure is constant, becomes P delta V. So we can say that the work done is constant pressure into change in volume, or it is also equal to nR delta T. So this is the first thing. This area under the graph, this is work done. So A to B, the work done is positive of the area, whereas B to A, work done would be negative of that area. It would be P into V1 minus V2. So that's a negative quantity. This would be P into V2 minus V1. That would be a positive quantity. Okay, so that's your path dependent quantity, work done. Now your state function, so this is your path function, whose formula we are getting according to the path on the PV curve or on the PV space. Now delta U is a universal formula because it's a state function. So now combining these two by first law of thermodynamics, we'll get NCP delta T, that is our Q, is equal to NF by 2 R delta T, that's our delta U, plus NR delta T, that's our W. Okay, so from this we are getting the term that Cp is equal to F by 2 plus 1 into R, or Cp is equal to Cv plus R. So that is the relationship between isobaric molar specific heat capacity and isochoric molar specific heat capacity. Molar specific heat capacity at constant pressure. Okay, so for isobaric process, the molar specific heat capacity is Cp, which is Cv plus R, or F by 2 plus 1 into R. So Q is equal to NCP delta T. W is equal to NR delta T, and delta U is equal to NF by 2R delta T. So this can also be written as this term. Okay. So because in general, so this is the situation about isobaric. Yes, Aman, that's correct. Maya's formula. Okay, so let's visualize an example problem based on an experimental kind of setup. So what we have here is, say we have a double walled container which is fitted with a free piston. And on top of that, we also have certain mass M. And now inside the chamber, there is sample of nitrogen gas, and there is some heating element like a heating coil by which heat can be supplied. So given, and of course this is what we call insulated chamber, or these are insulated walls, so there's no heat exchange. The piston is also insulated. The piston also does not conduct heat. Okay. So given the piston is massless, okay, and of area 10 centimeters square, or let's make that 100 centimeters square. Now initially the gas is in equilibrium, that is the piston is in equilibrium with x naught equal to 20 centimeters, and the temperature of the gas equal to 100 Kelvin. So the nitrogen gas inside is at equilibrium for this kind of situation. The mass on the piston that mass is equal to 100 kgs. Take G as 10 meters per second square. Now heat is slowly supplied through the heating coil till the gas expands and X increases from X naught equal to 20 centimeters to X equal to 30 centimeters. Okay. So find the final pressure, volume, and temperature after this process. Okay. Find the heat supplied, the change in internal energy, and work done by the gas for this process. Okay, try this out first, then we'll discuss the second part of the question also. Okay, another thing given is that atmospheric pressure is equal to 10 raised by 5 pascals. So we have to take this approximate value of atmospheric pressure and do this calculation. Just try this question out, people. So can anybody tell me what kind of process the gas is undergoing? What kind of process is the gas undergoing in this situation? Yes, Aman, very good. That's correct. Anybody else? Yes, Kevin, that's correct. Very good. Yes, very good, Vineet. That's correct. Correct, Naman. So anybody wants to explain why it is isobaric process? Anybody wants to answer the question, you can unmute yourself and answer. It's an isobaric process, right? So how do we know it's isobaric? What is the logic behind that? No, anybody wants to answer? Kevin? Yeah, that's okay. But how do we know? Unable to unmute. Okay, just a second. Yeah, try again, Kevin.
Yeah, so in order for the piston to be in equilibrium, the pressure of the gas has to be equal to the atmospheric pressure plus the mass of the the mass which is present on it. That's why the pressure of the gas is constant.
Yeah, so how we know the pressure is constant? Because the piston is free, no, basically.
Yeah.
That is the main thing, no? There is no
Yeah.
friction between the piston. So what will happen is equilibrium mein rahega piston always, no?
Yeah,
So
that's
the
right.
force the gas is applying has to be constant because you're not changing the mass. Plus the
Yes.
piston is free.
Yes.
Right. Okay. So because the mass is constant of the piston, so all of you understood, because the mass of the piston is free and we are not fixing the piston with any nails or anything. No? It's free. It's just floating on the gas. So that means the total weight of the piston plus the force that the atmosphere is applying on it because of atmospheric pressure, that has to be balanced by the internal pressure of the gas. Okay. So Vineet, hope you have also understood. It's correct that volume is increasing with temperature, but that is not just enough. No? We have to also understand how volume is increasing with temperature. It is increasing proportionately or not. Now, it can be increasing in a situation where it's not isobaric also. So when we will know that the volume is increasing proportionately and therefore it is this thing. No? Therefore it is a isobaric process. Only when we can confirm that the pressure is remaining constant. That means we are manipulating the gas in such a way that pressure constant है. So because it is a free piston, so at any point of time, the piston started from here. Let's say at this point of time, the pressure of the gas inside was P naught. The volume was V1 and temperature was T1. Now, this is a fixed mass. So the piston must be in equilibrium. So the force the gas is applying, that must be balanced by the weight of this thing plus the force that the atmosphere is applying. So F is equal to F naught plus mg. Okay. So F is internal pressure into area initially and atmospheric pressure into area plus mg. So the initial pressure of the gas is this, and if you calculate this, this is 10 raised power 5 plus I've given this as 100 kgs. So 1000 newtons divided by area of 100 centimeters square. E is the area of the piston. So that is how much? 100 into 10 raised power minus 4 meter square. So that is 10 raised power minus 2 meters square. So in pascals it becomes like this. So it's 2 into 10 raised power 5 pascals, or basically 2 atmospheres. That is the initial pressure. Okay. Now the thing is, from here, as we are supplying heat, the gas is going to expand because the piston is free. But at the new state also, what is happening? The free body diagram of the piston is the same. It's the same forces acting on the piston, mg, force F, and P1. So you can see that this pressure remains constant. Okay. So the gas is undergoing an isobaric expansion. So the first part is an isobaric expansion. Okay. From initial volume, which was x naught into area, to a final volume, which is x into A. So that we can now check out. 20 centimeters into 100 centimeters square. So okay, 2000 cubic centimeters. That's the same thing as 2000 milliliters. It's 2 liters to 3 liters. The volume is expanding from this to this at P equal to 2 atmospheres. Okay. So V1 upon V2 is equal to T1 upon T2. So the final temperature will become 3 by 2 times the initial temperature. So 150 kelvins. Okay. So at the end of the first process, yes, very good, Aman, that's correct. So it's going from volume of 2 liters, temperature of 100 Kelvin, to volume of 3 liters, temperature of 150 Kelvin, but constant pressure of 2 atmospheres. Isobaric process. Okay. So now we can calculate all these things. Delta U is of course N F by 2 R delta T. So that is now nitrogen gas. So degrees of freedom will be 5. So that is 5 by 2 nRT2 minus T1. So we can write that as 5 by 2 into P into V2 minus P1. So 5 by 2 into 2 atmospheres. So that's these many pascals into 3 minus 2 into 10 raised power minus 3. Sorry, 10 raised power 3. So minus 3 meter cube, correct. So remember 1 liter is 1000 cc, which is 10 raised power minus 3 meter cube. So this is in pascals, this is in meter cube. So this is becoming how much now? This is becoming, I think, 100 joules, right? Oh, sorry, 500 joules, my mistake. Yes, correct. Plus 500 joules. It's an expansion isobarically, so the internal energy is increasing. Okay. Q is equal to NCP delta T. W is equal to NR delta T. So that is T delta V. That is 7 by 2 into T delta V. So this will become plus 700 joules. This will be plus 200 joules. Okay. So for this isobaric expansion of nitrogen gas, just using the formula and keeping in mind that NR delta T is P delta V. Okay. So these are coming out to be these three quantities. Yes, Kevin, very good. That's correct. Okay. Yeah, you can. That's correct, Vaishnavi. Very good. So you don't need to apply all three formulae. You can just apply any two of these formulae. Okay. Any two of these, and then use Q is equal to delta U plus W. That's correct, Vaishnavi. Do that also. Okay. So there are so many things you can do now. You can also do it this way, that you can. Another alternate way of doing the question is that once you understood its isobaric, just visualize the graph. So you can see that pressure remaining constant at 2 atmospheres, so 2 into 10 raised by 5 pascals. The volume is changing from 2000 milliliters to 3000 milliliters. Okay. So this is going in this direction. So W is just area, positive of the area. So that's plus 200 joules. And then you have the formula that for isobaric process, okay. So if this is 200, this will become 7 by 2 times 200. Delta 2. Okay, so this is, sorry, 5 by 2. It's a diatomic gas. So you can use this also. Okay, so this is one of those subjects where you have a lot of options of doing questions by different methods. Okay. So anyway, hope this is clear. If anybody has a doubt, you can ask me straight away. Okay, now let's come to second part of the question. Now after x is equal to that 30 centimeters position is reached. Okay, the piston is fixed. Okay. So it is, let's say we have some mechanism of doing this. We put two nails like this, so the piston becomes fixed at x equal to 30 centimeters. So we fix the piston, and now further heat is supplied. Okay. And further heat Q prime is supplied till a temperature, final temperature of 300 Kelvin is reached. Okay. So find Q prime and delta U prime for this process. and find the final state. That is pressure, volume, temperature. Temperature obviously I've given you 300 kelvins. So in physics, like this is the type of language of questions you can expect. The question might not tell you directly that it is isobaric process, it's isochoric process. It will describe an experiment, and through the experiment's conditions, you have to figure out, like you did in the first part, that the piston is free, the mass kept on it is constant, so it's isobaric. So like that, you have to figure out what process is happening. So what type of process is this second one going to be now? Yes, that's correct, Shubham. Correct, Kevin. Aditya, correct. Very good. But can somebody tell me one thing? I have also mentioned that the walls of the container and the piston, they are non-conducting. No? They are insulated walls. Right? I mentioned that in the question. So how come the process is not adiabatic? Why is the process not adiabatic? Yes, very good. That's correct, Anushka. It's a trick question I asked, but your answer is correct. Good. It's very obvious. You've given the correct answer, but sometimes people miss this answer. So we are supplying heat through the heating element. Nee, Aman, see what is happening here. The walls are non-conducting. So the heat we supply, it doesn't escape out of the container. It keeps the internal energy increased. So that is where now what would have happened. Suppose we had fixed the this thing piston like we've done over here, but the walls are conducting. Okay, and the outside temperature is 300 Kelvin. So supplying heat up to 300 Kelvin, the gas would heat up. Okay, but first of all, it would have heated up initially only. Na? It could not exist at 100 Kelvin or 150 Kelvin because the walls are conducting. So heat would have come in. Okay, but suppose we want to heat it more than 300 Kelvin. We can't do that because the walls are conducting. Whatever heat we supply Q prime, it will just come out of the conducting walls into the atmospheric air outside. So that is why we have to keep the, yeah, that's the point. So that the heat we send in, it remains in the container, and also no other heat comes out from anywhere else, or no heat goes from inside to outside or outside to inside. That's why the walls are non-conducting. But we do have a heating element through which we are supplying heat in a controlled manner. So because we are supplying heat through the element, we cannot say it is an adiabatic process. Okay. So here what is happening? The piston is fixed. Okay, and heat is supplied. Heat is supplied. So fixed piston means fixed volume, means isochoric. Okay, and Q prime heat is supplied. So that means it is a isochoric heating. So going back to our earlier graph, now in the second part of my problem, the graph is progressing in this way. पहले तो मैंने isobarically उसको heat किया था. So it went from a volume of this much to this much. Now keeping the volume constant, I am heating it. So this is the second part of my experiment. went from a volume of 2 liters to a volume of 3 liters. But now I'm fixing. Okay. And I also saw that the temperature went from 100 Kelvin to 150 Kelvin. Now I'm bringing up the temperature to 300 Kelvin. Okay. So the second process is the isochoric fitting. So you can see that pressure is proportional to temperature. Therefore, P3 upon P2 is equal to T3 upon T2. So the final pressure is becoming 4 atmospheres. Final volume is same as this volume. So that's 3 liters. Okay. And final temperature was given to us. So this is the final state. So now we also know that okay, this pressure is 4 atmospheres. Now for this process, obviously we know Q is equal to delta U because work done is 0 in isochoric process. Which we can also write over here as F by 2 into V delta P, because if volume is constant, then V delta P is equal to NR delta T. This implies this, okay? So this NR delta T is the constant volume of 3 liters into the change in pressure. So plus 600. NR delta T is plus 600 joules. Substitute that here. So just check my answer. Are you getting the same? For the second process, should be getting this. Yes, very good, Shubham. That's correct. Okay, so hope this question is clear, people. Okay, now before we proceed to other things, just one interesting observation I want to show you, that on the PV graph, okay, we can manipulate the parameters and make the gas go in a direction which is horizontal. In that case, it would be isobaric. Then we can again manipulate the parameters, make it go vertical. Then again, we can manipulate the parameters, make it go horizontal. So we can manipulate the experimental parameters in such a way that we can make it go along any path. So any general path that we want, any arbitrary path, we can achieve it by making small differential changes that we can manipulate. Okay. So that's why any quasi-static process can be reversible also, because we are going from point to point and each point is in a state of equilibrium. So So whatever order we did for these differential changes to create this path in one direction, we can do the reverse of those small changes and the path will simply reverse itself. So that is why as long as the gas is behaving in such a way that going from the initial state A to the final state B, it is actually going through each point in the curve in between. And each point is defined by a proper equation of state that PV is equal to nRT at that particular point. So the process can always be reversed exactly by the same path. Okay, so that is the theoretical logic of why quasi-static process is reversible by definition. Any and every quasi-static process is reversible. Okay, so hope this point is clear to all of you. Okay. Now next we'll see if we have a situation like this where we have conducting walls. So this is, let's say, a metallic container. Okay. And we have a free piston which we can load with some kind of material like sand or concrete or whatever. Okay. So if the mass m is slowly increased, what will happen? Work is done on the gas. Okay. So what will happen is this will, if I make this m plus delta m, so it will push down. Okay. But in the process, some heat will come out because the gas's temperature will remain constant, the temperature outside, because it is conducting in nature. So work is done on the gas, heat will get absorbed by the atmosphere from the gas. Okay. And delta U will remain zero because temperature will remain constant. So this is an example of isothermal compression. This is how we do it in the physics lab. We want it to go through that isothermal curve very slowly. So we'll keep on adding mass very slowly. So the gas goes from one equilibrium state to a new equilibrium state. So initially when we add the mass over here, the gas's temperature will tend to increase a little, but immediately some heat will come out and the temperature will stabilize to the temperature outside. So it will come to a new equilibrium state where it is isothermal with respect to the earlier one, but the volume has reduced and the pressure is increased. So it has undergone a very small isothermal expansion, compression. Then we'll add more mass, and like that, adding very little mass at a time, we are able to achieve that very slow reversible quasi-static process, which will be along the isothermal curve. That is, it will be along the curve where pressure is proportional to temperature. So this is the direct physical example showing you how to achieve an isothermal compression. Now, similarly, if we remove mass very slowly from the piston, if mass is removed slowly from the piston, then the gas will tend to expand. Okay. And it absorbs heat from the gas absorbs heat from the atmosphere around. So work is done by the gas. Okay. And Q is absorbed by the gas. So it is, heat is supplied by the environment to the gas. So both these are examples of, okay, but temperature remains constant. So both these are examples of isothermal process. Okay. This one is a expansion. This one is a compression. So from the experimental point of view, this is how we can achieve isothermal, perfectly isothermal quasi-static process. We can achieve this by removing the mass very slowly to make it expand, or adding mass very slowly to make it compress. And if we keep a thermometer inside to constantly monitor the temperature of the gas, we'll see that when we add or remove mass for a very short duration of time, there might be fluctuation, but the temperature stabilizes. So we can go on plotting the points on a PV graph for the stabilized points, and we'll see that if we go on plotting those points, we will achieve the isothermal curve, which is the hyperbolic curve of P is inversely proportional to V. So you have to have this visual picture of the experimental method as well as the understanding of the graph. If these two things are clear, rest of them are very easy. With practice, you will know where to apply what formula. And always try to understand the formula from the logic starting from kinetic theory of gases. Don't try to blindly memorize the formula. Just understand first law is like a statement of work energy and how the logic of that statement of work energy applies in all these different situations. Whether I'm keeping the piston fixed so its volume is constant, so I'm not allowing the gas to do work or do work on the gas, or I'm allowing the piston to move freely but I'm keeping the mass on the piston constant, so the pressure always remains stable, so it's isobaric. So logically like this you understand. The rest you'll find it's a very scoring subject. You can score 100% of the marks that come from heat and thermodynamics in JEE in physics. Is not too difficult to do compared to mechanics or electromagnetism. Of course, the weightage is also less, but you can look at really boosting your physics score with all these type of topics like heat and thermodynamics, optics, modern physics, to a certain extent, sound, waves and sound also. These are like very scoring topics. So it can really boost your rank. Okay. So these were examples of isothermal. So formally, when we look at isothermal by definition, it is where temperature is constant. Okay. Or change in temperature is zero. Yeah, Vinith, I'll scroll up. Okay, finish writing down this portion. We'll understand the formula and things in a moment. Okay, very good. So let's now look at the equations and things. So if change in temperature is zero, so that immediately tells us that internal energy is not changing in an isothermal process. Internal energy remains constant. So that is why, as we have seen logically above, that either we supply heat and the gas does that much work, or we absorb heat from it by doing work on the gas. Okay. So if Q is positive, W is positive. So heat is supplied and the gas expands. Or Q is negative, W is negative. So heat is absorbed from the gas and it contracts or compresses. So now the interesting thing is that there is no such thing as molar specific heat capacity, because C is equal to Q divided by N delta T. Now here what is happening? Q is non-zero, but delta T is zero. So C is undefined. Molar specific heat capacity is undefined for isothermal process. Instead, we define it from this relation. Q is equal to W is equal to integration PdV. Okay. So that becomes integration, as you know, nRT, which is a constant, from initial to final. So Q is equal to W is equal to nRT, natural log of final by initial. And as you can logically understand, this quantity will be positive when final volume is greater than initial volume, because ln of x is positive when x is greater than 1, negative when x is less than 1, 0 when x is equal to 1. So from that you can understand that when final volume is greater than initial volume, that is expansion is happening, so work done is positive, as it should be logically. Okay. So the final thing about the isothermal process is the graphical representation on PV space. So it's a rectangular hyperbola. Okay, so this area we've calculated by integration. This B2A would be a compression, negative of the area. Okay, now another important point I wanted to be aware of is that when we divide or when we draw isotherms at different temperatures for the same given gas sample, how they look in relation to each other. So for n number of moles of an ideal gas, if we draw an isothermal curve or an isothermal processes curve, it is called an isotherm. If we draw an isotherm at some temperature, let's say T1, Okay, and then we draw another one at a different temperature. They look like a series of rectangular hyperbolas, such that the way I am drawing them, the temperature is increasing. As you go away from the origin, the temperature is increasing. Okay, so T naught is less than T1 is less than T2. So you can think of the entire PV space as a grid of isotherms across PV space. So any particular point, it lies on a particular isobar, so it has a particular pressure. It lies on a particular isocore, so it has a particular volume, but it also lies on a particular isotherm, so it has a particular temperature. And no two points will have all three coordinates the same. Pressure, volume, and temperature. These are this is the unique state of a gas at a unique point in the PV space. So every particular point on the PV space, it lies on a unique combination of the intersection of isotherm, isobar, and isocore. So it has the three values are unique. Two points might have same pressure, might have same volume, okay, but all three coordinates will not be same for two different points. Okay. Now, likewise, we have the fourth and final process, which is the adiabatic process of the named processes. Now, this is one where by definition, there is zero heat exchange. So neither heat is supplied nor heat is withdrawn. Q is equal to 0. So experimentally, this would have to be done in this way, that you have the insulated vessel with the insulated piston, and you don't connect any heating element or anything. You just manipulate the state of the gas by manipulating the mass on the piston. Okay. So this is an insulated, these are insulated walls or non-conducting walls. Okay. This is a free but insulated piston. Okay. So by increasing or decreasing mass slowly, the gas is compressed or expanded adiabatically. Okay. So when we compress the gas, work is done on the gas. Okay. And internal energy increases. Whereas when we let the gas expand by removing mass, work is done by the gas. As a result, the gas will cool down. Its internal energy change will be negative. So its temperature will drop. Here its temperature will rise. So adiabatic compression, remember, results in temperature rise, and adiabatic expansion results in temperature drop. So Q is equal to 0 means delta U plus W is 0. And molar specific heat capacity is 0 for adiabatic process. Because Q is 0, but delta T is non-zero. So adiabatic molar specific heat capacity, if the question arises ever, its value is how much? 0. But isothermal molar specific heat capacity, it is an undefined quantity. Okay, now it comes to the relation between pressure and volume. So PV graph for an adiabatic process. What is called an adiabat or adiabatic curve. Okay. So on the one hand, you have PV is equal to nRT, which we write in differential form as PdV plus VdP is equal to nRdt, because pressure, volume, and temperature, all three are variable here. Only number of moles is fixed. Okay. Then you have your ideal gas equation, but for adiabatic process. So Q is 0, so delta U plus W is 0 because Q is 0. So that can also be written like this in differential form. So that is NF by 2 RDT plus PdV is 0. So this is my equation 1, and this is my equation 2. Then this nRdt can be substituted here, and this becomes F by 2 into PdV plus VdP is equal to 0. Okay. Now you know that Cp is equal to F by 2 plus 1 R, and Cv is equal to F by 2 R. So we can also say that Cp times dV by V is equal to minus Cv times dP by P. We introduce a new constant, this is called the adiabatic constant. Okay, so we integrate this from some P1 to P2, while this is from V1 to V2. This become a term like this, and from this we can see that so P is inversely proportional to V to the power adiabatic constant. So this is how we derive the relation for the adiabatic curve, or the equation of the adiabatic curve. Okay. Now just a few additional relations that you should keep in mind, that CV, which we write as F by 2R, can also be written as R upon gamma minus 1, because okay, so the inverse of this becomes this Cp, which is F by 2 plus 1 R, becomes gamma R upon gamma minus 1. So these two additional formulae you should remember. So delta U for any process, which is NF by 2R delta T, can also be written as NCV delta T, can also be written as NR upon gamma minus 1 delta T. And the other thing is that the graphical representation, the PV curve for an adiabatic process, it's easy to understand that it's hyperbolic in nature, but one should also understand its relation with respect to isotherms. So this is an equation of adiabat. P is proportional to 1 by V to the power gamma. Then in comparison to that, the isotherms will be looking something like this. They are gentler in curvature. Okay. So that if you are undergoing an expansion adiabatically, you can see that your temperature is decreasing. So this point is A, this point is B. You can see that temperature at A is greater than temperature at B. So A to B is an adiabatic expansion. It results in temperature drop, whereas B to A, adiabatic compression, that results in a temperature rise. Okay. And finally, one more thing, PV is equal to nRT, and PV to the power gamma is constant for adiabatic process. So from this you can see that it is constant, or yes, Kevin, I'll scroll it. But I'm going through this a little fast because I'm assuming that you are familiar with most of these things from chemistry also. So we'll focus mostly on solving questions rather than the derivations. You have done these derivations, right? Okay. And you must have done polytropic process also. Yes. So yeah, so you'll be familiar with these things. So just one round of problem solving and you should become quite efficient at this. Okay, Kevin. Okay, so this part is clear, na? How the adiabatic curve looks in comparison to the isotherms. These are isotherms. This is at this one is at a temperature B, so you can see. So the adiabatic curve has a sharper slope than the isothermal curve because gamma is greater than 1. Okay, so let's move on to a question next. So a sample of a monoatomic gas at initial pressure of half an atmosphere, volume of 4 liters, and initial temperature of 100 Kelvin, okay, is adiabatically compressed to a volume of 0.5 liters, okay, and pressure P2, temperature T2, followed by an isothermal expansion back to, oh sorry, followed by an isothermal expansion okay, and finally an isochoric process back to T1, B1, T1. Okay. So first of all, plot the three processes in a PV graph. Then find P2, T2, P3, V3, P3, and Q delta U and W for each of the processes. Each of the individual processes. We will not do this like a cyclic problem yet. We'll come to uh, cyclic processes in a bit, and they will understand what is the difference between saying what is Q net for the cycle versus what is Q for each of the processes that are part of the cycle, or what is W net for the cycle versus what is W for the individual parts of the cycle. Here we are only interested in the individual parts. It consists of one adiabatic process, one isothermal process, and one isochoric process. But there is something to learn in this, and by visualizing the graph only, you will be able to solve one part of the question where there is no direct hint given to you. The three things P3, V3, and T3, how you have to figure that out, that will ultimately you'll understand that from the graph. So just start by trying to understand, trying to visualize how the graph will be plotted over here. Okay, so what about P2 and T2? Must have got that by now. Monoatomic gas. So degrees of freedom is 3, so gamma is 5 by 3. So use that relation. Yes, very good, Aman, that's correct. Yes, Naman, both the answers are correct. Yes, Aman, that's correct. Okay, so for the adiabatic compression, we're going from okay, so these values are we start by using this. And express 8 as 2 cube. Okay, so that's how we get the pressure as 16 atmospheres. Okay, and then you can just use P1 V1 upon T1 is equal to P2 V2 upon T. So we get this temperature as four hundred. Okay. Yes, very good. Aman, that's correct. Now, since you are having to come back isochorically, so you'll have to expand to 4 liters from here. So basically, the important thing is now from this state, you are going isothermally. Okay. And then from whatever state you are there, P3, V3, T3. Now, T3 is obviously equal to T2 because it's isothermal at 400 Kelvin. Okay. But from here, you're coming back to this state isochorically. If you're coming back to this state, your volume has to be 4 liters. Okay. So that is what now tells you that, okay, this should be equal to 4 liters. This tells you this. And this tells you this. Okay. So now in the isothermal process, where pressure into volume is constant. Okay. So that's why your pressure will become. So the volume is becoming 8 times. So the pressure will become 1/8. Two atmospheres. So that's coming from here. Okay, so I'm sure this is clear to you. We'll quickly go over the graph for the entire cycle. Graph will also give us some perspective about the relationship between isotherms and adiabats. So our first process is an adiabatic compression. Let's say that is this one. So this is our P1, V1, T1 to P2, V2, T2. This is adiabat. Okay. Then remember our last process is going to be isochoric. So it's like from here, if we are going along an isotherm, we have to go like this somewhere, let's say. But the moment that isotherm you reach a position where you're back to the original volume, that is this volume of 4 liters, you know that you have to stop there, because so this is your point P3, V3, T3, because from there you have to come back isochorically. So you don't have an option but to go through the vertical line now. From here to here. This is isochoric, this is isothermal. Okay. So basically you're cutting between these two isotherms twice. Once you're cutting from the lower isotherm at what was it, 100 Kelvin to the higher isotherm at 400 kelvins, but adiabatically. And then later you're cutting back from 400 to 100, but isochorically. So that is this. Now for each of the processes, for the adiabatic process, see Q is 0, delta U is equal to, so that is monoatomic gas, so 3 by 2 into P2 V2 minus P1 V1. Okay. And we have just seen that this pressure was 0.5 atmospheres. So this pressure was becoming 16 atmospheres. Because this volume was half a liter. So delta U is going to be positive. 16 into 0.5, that is 8, minus 0.5 into 4, that's 2. Okay. So 10 raised by 2 joules. Okay, so this is a adiabatic process. Q is 0. So W is equal to minus delta U. These are the quantities. Okay. 1 atmosphere is approximately 1.01 into 10 raised power 5 pascals. 1 liter is exactly equal to 10 raised power minus 3 meter cube. So that's why 1 liter atmosphere is approximately 101 joules. All right, now the second process is isothermal. Okay. So in that, what is happening? Our delta U is 0. So Q is equal to W is equal to nRT natural log of final by initial. So we can write nRT as just P2 V2 or P3 V3, whatever. Okay, so P2 V2 is 16 into zero point 0.5 liter atmosphere, and this is 4 divided by 0.5 in liter atmosphere. So that is 8 ln 8 into 101 joules. So second process, Q equal to W will be this, okay, and delta U will be 0. And ln 8 we can always write as 3 times ln 2. So 3 into 2.303 log 2. So approximately that will become 3 into 0.7, 2.1. So ln 8 has an approximate value of 2.1. So this is approximately 168, 16.8 into 101. So something like 1680 joules. Okay. And the final isochoric process is very easy. In that W is 0. So Q is equal to delta U is equal to, okay, so that is 3 by 2 into V delta P. So Q and delta U will be negative quantities. Okay. And, remember this pressure had come out to be 2 atmospheres. Okay, so this is in liter atmosphere. So you can just check my calculation once, but I'm getting it. Is this for the third process? Yeah, it seems about correct. Okay, so this is what comes under the category of the easier questions in first law of thermodynamics applications, because you can basically do them formula based or formula wise. You just understand how to connect the different variables. So on the one hand, you always make use of equation of state PV equal to nRT, and on the other hand, you always make use of the properties of the four standard processes, that either volume is constant or pressure is constant or Q is 0 or delta U is 0 because temperature is constant, whatever. And accordingly, you understand where to apply what formula. Try not to do it by rote learning and try to always understand the applications from the definitions of the different type of processes and the concepts behind those definitions. Then, okay. So we'll conclude here, but just giving you a quick heads up on our next lecture. But before our next lecture, we have a doubt session. So as I told you in the doubt session, my first priority will be any questions from MT7, and then any other questions from heat and thermodynamics, or even the portion before that, work by energy, etc. Okay. Or any other questions in physics, you can ask me. That's not a problem. Okay. And now next up, we will be doing in heat and thermodynamics, we will be doing polytropic processes, which is basically like a family of curves in the PV space. So PV to the power alpha is constant, where alpha is any real number. So it is like a family of curves. Okay. So for example, if alpha is 1, then you actually get an isothermal process. If alpha is 0, you actually get a isobaric process. But if alpha is, for example, minus half, then this is a process where P is proportional to root V. Okay. Or PV to the power minus half is constant. So that will mean this here. So this process will look like this sort of a process. So for these processes, we will develop the general formula that work done is nR delta T upon 1 minus alpha, and molar specific heat capacity is Cv plus R upon 1 minus alpha. So Q is equal to Nc delta T. So these two will give us direct formulae, which we'll be able to apply in any equation of this type. Okay, so that's one thing we'll look at next time, and also we'll look at cyclic processes and through that heat engines. Okay, we have already seen one example of a cyclic process today. So that's what we'll look at next time. Okay. So anyhow, that's it for today's session, people. Wish you all the best, and make sure you have collected your doubts and kept them ready during our doubt session so we can discuss maximum of those. You can keep sending me doubts also, otherwise it's not a problem. So all the best and thanks for attending, people. Wish you all the best. Yes, I will try to do that, Vineet.